Hi, welcome to the second tutorial, Solar Radiation Variations. This relates to the syllabus Changes in the Global Energy Balance, Solar Radiation Variations, including global dimming due to volcanic eruptions. When we think about changes in the global energy balance, I think it's really important to be thinking about, well, what factors are going to have an impact on those inputs into the atmosphere, those storages within the atmosphere, and that interaction between the Earth's surface and the atmosphere. Now, the biggest impact on the global energy balance relates to the Milankovitch cycles. This was first theorized by Milutin Milankovitch, a Serbian geophysicist, and he identified that solar radiation coming into the atmosphere is impacted by three key factors: centricity, obliquity, and precession. Now, with eccentricity, what we're concerned with here is the Earth's orbit around the Sun, and it switches from being circular to more elliptical. Now, the amount of solar radiation reaching the Earth's surface doesn't vary significantly between those two types of orbit. But what we get is, with a more circular orbit, we get a more balanced quantity through the year. And with an elliptical orbit, we get this big difference between increased insolation and reduced insolation as the Earth is furthest away. Now that impacts the amount of energy reaching the Earth's surface and the spatial distribution of that energy reaching the Earth's surface. And those changes there are significant, and they can lower the Earth's temperature, and they're quite associated with ice ages, those 100,000 year period ice ages that the Earth follows. The second Milankovitch cycle refers to obliquity. This is the tilt of the Earth's on its axis, which is currently 23.5 degrees, but it switches between 22.5 and 24.5. So that small switch in the axes, the tilt of the Earth, will take the northern hemisphere closer to the Sun, slightly further away, pushing the southern hemisphere closer to the Sun, slightly further away. So those surface differences are going to impact the amount of absorption of solar radiation. And finally, the third of the cycles is precession. This is the Earth's rotation on its axes, and this is thought again to have impacts on the distribution, the spatial patterns of solar radiation reaching the Earth's surface. The Earth kind of wobbles on that precession, and it has increased periods of wobble and decreased periods. It's also very important here to remember that these cycles don't necessarily increase or reduce solar radiation. They just change that pattern of where it's coming in and how it's interacting with the Earth's surface. So we can see actually on this slide those same cycles, and you can see the time frames they're most associated with. So we see eccentricity 100,000 years, precession 26,000 years, and tilt or obliquity 41,000 years. So another factor that influences changes in the energy balance are sunspots. These are a little bit sort of unclear in terms of their exact impact on atmospheric temperature. But what takes place over 11-year cycles, we get increased sunspot activity on the sun's surface. So sunspots are a temporary phenomena. They appear as darker spots on the surface of the sun, and they're regions of reduced surface temperature caused by concentrations of magnetic field flux that inhibit convection. So periods of time where you have high sunspot activity, well, this is associated with increased energy output from the sun. So ultraviolet radiation increases during high sunspot activity, and this can have a large effect on the Earth's atmosphere. The actual exact impact on temperature is seen to be unclear, but reduced sunspot activity associated with slightly lower temperatures, higher sunspot activity, increased temperatures. So it's quite easy to understand, I think, when volcanoes throw out ash, that ash can block incoming sun, incoming solar radiation. And so ash does do that. It dims global temperatures. But that's not the only thing that's going on with eruptions. So when volcanoes erupt, they produce sulfuric gases, and these can convert to sulfate aerosols. And these are a really efficient absorber and reflector of solar radiation. And so on this graphic here, we can see at the bottom left corner, we see that impact on global temperature. Starting with Krakatoa and Santa Maria, you see very clear falls in temperature on the graph. But we also see that it takes a significant amount of time for temperatures to recover to get back to what might have been mean temperature. So Santa Maria as well, a significant fall in global temperature, but quite a significant time lag before it reaches mean temperature again. Agung here, a lag in recovery. So these eruptions produce huge quantities of sulfate aerosols, and these are very, very efficient absorbers of solar radiation.